Suppose we have a wire that is carrying a current in a magnetic field. Because current is moving charge, those charges are generating their own magnetic field. And since those charges generating their own magnetic field are inside of an external magnetic field, the two magnetic fields will interact to create a magnetic force. So we could say that the magnetic force due to a magnetic field B exerted on a current-carrying wire of length dl, or L rather, is given by the integral of current with the cross product of a displacement differential with the magnetic field. Let's use this to do an example. The high voltage power lines that carry electricity across great distances carry very high currents as well. Suppose we have a direct current power line near the equator, where Earth's magnetic field is parallel to the ground. The wire carries a current of 850 amps to the east. The length of cable between adjacent towers is 400 meters. What is the magnitude and direction of the force of Earth's magnetic field on this length of wire? Now, the magnitude of the Earth's magnetic field near the equator is about 5.0 times 10 to the minus fifth Tesla. So in this example, we are looking at a current-carrying wire near Earth's equator. So this current-carrying wire goes between two towers. So let's illustrate those towers here. And this will be the wire that we are going to investigate. There's probably at least two wires, but we're going to focus on one of these wires. So this wire has a length of L, and that length is given as 400 meters. Now this wire is carrying a current to the east, so let's go ahead and establish our coordinate system. We will say that our coordinate system is established such as the right corresponds to the east direction, up will correspond to the y-axis, and pointing straight away from us will correspond to the north axis. So I'll illustrate that with just this line right here, and that is really representing a direction that is going straight away from us or into the screen. So with that direction established, we know that the magnetic field is going northward. So since the magnetic field is going northward, I am going to illustrate that with a series of x's, where each x represents a magnetic field line that is pointing straight away from us or in the direction of north. And we know that the magnitude of the magnetic field is given as 5.0 times 10 to the minus fifth Tesla. Also, this wire is carrying a current I. So we will illustrate the current I going to the right, which is the eastward direction, and the current is given as 850 amps. Using this information, we have to determine the magnitude and direction of the magnetic force on this length of wire. So the formula for the magnetic force on a current-carrying wire is given as an integral over the length of the current in the wire with the cross product of a displacement differential in the direction of the current and the magnetic field that the wire is inside of. Now this integral is going to take place over the length of the wire, so it is going from 0 to L for the limits of integration. We know that the current is constant, so we could pull that outside of the integral, and we have the integral of the cross product with the displacement differential and the magnetic field. Now, the magnetic field is also uniform. Because the magnetic field is uniform and we know both the direction of the current and the direction of the magnetic field, let's use the right-hand rule and the fact that we know what the value of the magnitude of the cross product is to rewrite this integral. We could rewrite this integral to say that it is the integral of the magnitude of the magnetic field times the sine of the angle between the magnetic field and the displacement differential times the magnitude of the displacement differential. And this is going to be in a direction given by the right-hand rule. Let's go ahead and move this over to the left a little bit to give us a little bit more space to work with. So with this, we know that the magnetic field is a uniform magnetic field. So that means we could pull that outside of the integral. And we have the integral from 0 to L, the sine of the angle between the magnetic field and the displacement differential, dl, and again, the direction is going to be given by the right-hand rule. So what we have to figure out right now, which is going to be pretty easy to do, is the angle between the magnetic field and the displacement direction. Now that's pretty straightforward because we know that the current is going to the right and the magnetic field is northward. Well, the north axis and the east axis are perpendicular to each other, and that's an angle of 90 degrees. So this means that the sine of 90 degrees is equal to 1. And this allows us to write that the magnetic force on this current carrying wire is equal to IB times the integral from 0 to L dl with the direction given by the right-hand rule. When we integrate this, we get the integral of IBL with the limits of integration from 0 to L, which means that the magnitude of the magnetic force is just IBL, and we're going to have to use the right-hand rule to figure out the direction of the magnetic force. I can see that the right-hand rule is going to tell us that the direction of the magnetic force is going to be upward in the y direction. But let's go ahead and look at that. We have the current going eastward. So this is the direction of the current, which means a current element is also eastward, dl. We know the magnetic field is going straight away from us, so we'll represent that with an x. Now, to use the right-hand rule, we're going to have to apply it to the cross product between the displacement differential and the magnetic field. And so remember what that is going to be is we're going to place the fingers of our right hand in the direction of the displacement differential. We're going to curl our fingers toward the magnetic field, and when we stick our thumb out, the thumb will be the direction of the magnetic force. So let's go ahead and illustrate that. We'll start by putting our fingers in the direction of the current, which is to the right. We will then curl our fingers towards the magnetic field. Now the magnetic field is away from us. So that means we are curling our fingers away from us, and notice the direction that our thumb is pointing. Our thumb is pointing straight up. Since our thumb is pointing straight up, that is going to be the direction of the magnetic force. So that means that the magnetic force has a magnitude of the current times the magnitude of the magnetic field times the length of the wire, and it is in the positive y direction as based on our coordinate system. So let's go ahead and plug in our values now. It is a 850 amp current. The magnetic field has a strength of 5.0 times 10 to the minus 5th teslas, and the length of the wire is 400 meters. So let's do a unit check before we plug this into our calculators. On the left-hand side, we have force, so that's the unit of Newton. So we're looking for Newton on the right-hand side. On the right-hand side, we have an amp, a Tesla, and a meter. Remember that 1 Tesla is equal to 1 Newton per amp meter. So this means that we have an amp on the right, a Newton per amp meter on the right, and a meter on the right. So I see here that the amps cancels with the amps, the meters cancels with the meter, leaving us with a Newton on the right side, which confirms our units. Now we're ready to plug this into our calculator. Since our units check, I feel pretty good about the work we've done. After plugging it into my calculator, I get that the magnetic force on this wire is 17 newtons in the y direction, and in the y direction is just upward from Earth's surface.